In this video, we discuss learning outcome number 6 from lesson 4.2, which is all about the principle of redundancy and its relation to reliability. We're going to use the multiplication rule here in problems related to this application. So here's the principle of redundancy. The principle states this: we want to include multiple components that will all serve the same purpose, so that if one of those components fails, the entire system still runs as it should. So this is a principle that's used when you're designing something. Basically, the idea is you want to have a backup. You want to have something that can basically support the whole system, even if other parts of the system will fail. This is used to increase the reliability of many systems. So here are a few examples. The first one is just your eyes. So let's say you have a problem with your left eye. You're going to be okay because your right eye works. This one, you have a problem, the other one works. So you're good. You're good to go either way, because you've got these two eyes. It's redundant. Or if one of them has a certain problem, like maybe you've got like astigmatism or something, then the fact that you have another eye to support you means that together you can see better. You can see better. So that is an example of passive redundancy. Also in engineering, aerospace is an excellent example, and they show you an example regarding aerospace and aerospace engineering and designing airplanes in the textbook. But the idea is this: that if you have more than one engine and one of them fails, well, you're going to be okay because you have another engine to back you up. And we're going to talk about computer hard drives and backing up right now in our example. But the idea is if you have backups, it actually makes things much less likely to all fail at the same time. And since they're not likely to all fail at the same time, your whole system should run smoothly and it should run okay, even if there are some problems. So this is a problem that was modified from our textbook. I'll just read it to you. It says, it's generally recognized that it's wise to back up computer data. Assume that there is a 3% rate of disk drive failure in a year, and this is based on various sources, including lifehacker.com. In question A, we're asked, if you store all of your computer data on a single disk, what is the probability that the drive will fail during a year? Then we're asked, okay, well, if you do that, if you not only store it on your computer, but you also back it up on a second disk, what's the probability that both fail? And then lastly, what's the probability that 3 hard drives would fail? If you said, I don't just have this backup, I have the backup of the backup, and now I've got 3 versions, 3 copies of the same thing. What's the probability that all 3 will fail? Let's work this problem together. I've got this little image over here that I found online. It says, don't forget to back up. We're going to justify that. If you've ever thought to yourself, why does it matter that I back up? I've already got it here. I mean, that could fail too. Why should I have 2 versions of the same thing? That seems wasteful. It's actually not wasteful. It's actually an application of the principle of redundancy, and it makes you much more likely to lose your data. Okay, so here's part A. It says, if you store all of your computer data on a single disk, what is the probability that the drive will fail during a year? Well, they actually gave that to us already. They said, assume that there is a 3% rate of disk drive failure in a year. Okay, so the rate is 3%. So that's our probability. It's just in the form of a percentage and not a decimal. So we've got to move that decimal over twice to its decimal equivalent, and we have the probability of a single drive failure is 0.03. So 3% in decimal form. Now the question says, okay, well, what if you decide to back up? Everyone says you should back up. If the second disk is going to fail or potentially could fail at that rate of 3%, and the first disk fails at that rate of 3%, what's the probability that both fail? Well, we've got to use the multiplication rule because you're talking about one failing and then you're talking about another one failing. So we're going to take the probability that this single drive fails, and we're going to multiply by the probability that the second drive fails, provided that the first drive fails. Now, it turns out that these are completely independent events. The first drive failing has absolutely nothing to do with the second drive failing, so we don't really have to worry about that. So we're just going to take that 3%, we're going to multiply it by each other, and so we have 0.03 times 0.03, and that's 0.0009. I don't know if you know how small that is. We were talking about 3% before. 3% rate of failure if it's just your computer. And that's an assumption based on some data that can be found online. But suddenly, if you've got at second drive, the rate of failure is no longer 3%, it's 0.09%. That's less than 1/10 of a single percent. That's tiny. Less than 1/10 of a percent that you will lose everything on your computer. So having a single backup is great. Then you have a more than 99% chance that everything is going to work out just fine and you're going to have your data. Now, what if you say 0.09% is not good enough for me? I want to be really sure that I don't lose everything. Well, then you could use 3 hard drives if you wanted to. The question says, what's the probability that all 3 would fail? Well, you're just going to do exactly the same thing. You're going to use that multiplication rule again. You're just going to take the probability that the first one fails and multiply by the probability that the second one fails, provided that the first one fails. And then you'll multiply by the probability that the third one fails, provided that the first 2 fail. I actually had to make the font really small so that it could all fit on the slide. But again, that second drive failing has absolutely nothing to do with the first drive failing. And the third drive failing has nothing to do with the second drive failing or the first drive failing. They all fail at the same rate. They all fail at this 3% rate that's in the problem statement, provided our assumptions are correct. So we use the multiplication rule. You're just going to take 0.03 times 0.03 times 0.03, and then you get this number. It's hard to imagine how small that is. If you move the decimal over twice, you get a percentage rate of failure of 0.0027% failure rate. That's nothing. That's 27 in 10,000 percent. That's 27 out of 10,000th of a percent. That's small. So I think you're going to be fine, and you'll have all of your data when you're done. If you back up, see how quickly that 3% became less than 1/10 of a percent, and how that less than 1/10 of a percent became 0.0027, is less than 3/1000ths of a percent. All that was required was just having a backup and then having another backup in order to make it very, very unlikely that all 3 would fail at the same time and you'd be out of luck. So that's the principle of redundancy. You see that it leads to reliability of a system, and it's a great example of why you should back up your computer. On this last slide, we're going to summarize lesson 4.2, which is all about 2 rules, the addition rule and the multiplication rule. Now, the addition rule says that if we're trying to find the probability that A occurs or B occurs or both occur, you just add the probabilities. If you see or, think addition. If this happens or this happens, think addition rule. Now, when you add these, addition rule means you add the probabilities. You want to be careful. You want to make sure that you're adding in such a way that every outcome is only counted once. So you're going to take all the ways that A can occur and all the ways that B can occur, and then you divide by the total number of outcomes. But you have to be careful. Like, if you counted all the ways that A could occur and all the ways that B could occur, but there was some overlap, you accidentally counted that overlap twice. If you don't want to count that overlap twice, you've got to take it out. You've got to take it out at least once. Well, you're going to have to take it out exactly once, not at least once. So if you want the probability that A occurs or B occurs, you take up the probability that the first one occurs and you add the probability that the second one occurs, and then you subtract the probability that both are occurring at the same time. So that is what the addition rule says. And again, that subtracting the probability that A and B occur is just making sure you count everything once rather than accidentally counting them twice. Now, the multiplication rule allows us to find the probability that A occurs and B occurs. This rule has everything to do with the sample space. If you look at the sample space for the probability of A and the sample space for the probability of B, and then you want to look at the sample space for the probability of A and B, it's closely related to the probabilities or the sample spaces for A and B. I made a little video about that. It is separate from the PowerPoint slides, but it's material covered in the book as well. But it gives you a rationale and a justification for why you would want to multiply these probabilities together. But again, if you see that word "and," this happens and this happens, or both this and this happen, or all three of these happen, or this, and this happen. Anytime you see "and," think multiplication rule. You're going to multiply the probabilities. So the idea is you're going to multiply probability of A and probability of B, but be careful. That probability of B may need to be adjusted. We need to use the probability of B given that A has already occurred. And sometimes the fact that A has already occurred doesn't matter. That's when the events A and B are independent from each other. But there are other times when the probability of event A does affect the probability that event B occurs. If the probability, or if event A occurring affects the probability of B, we say that the events are dependent and that probability of B needs to be modified just a bit. We need to assume that A has already occurred, and then we say, okay, given that A has occurred, what is the probability of B? And we talked about that in the last video. So that's the addition rule and the multiplication rule. And I will see you in the next lesson.